Oftentimes in electronic design, we want to be able to regulate voltage and current to a specific value that we can designate and control. In the next few slides, we're going to show you exactly the methods to use to be able to do this. The first rule is called the voltage divider rule. It's also known as the potential divider rule. It's a simple circuit that produces an output voltage that is a fraction of the input voltage. That fraction is defined by a ratio of two resistors in series. It allows you to define how much potential you want at your output. To be able to execute this rule, you will need two resistors in series with an independent voltage source. In this case, V out, which is the voltage drop across a resistor R2, equals R2 over R1 plus R2 times Vn. If we wanted to find the voltage across R1, so VR1, the equation would be R1 over R1 plus R2 times Vn. So essentially, the voltage divider rule is just the resistor that you want the voltage across on the numerator over the sum of the resistors times the input voltage. In a similar way, we can also define the current by a ratio of resistors times the input current. This rule is called the current divider rule. A current divider circuit is a simple circuit that produces an output current that is a fraction of the input current. The difference between the current divider rule, and the voltage divider rule is the resistor that's on the numerator. In the current divider rule, you actually use the opposite resistor to which you want the current flowing out of. So I1 is found by the input current times R2 over R1 plus R2, and I2 is found by the input current times R1 over R1 plus R2. So let's think about this practically. What if we want to cut our voltage or our current in half? It's actually pretty simple. You just set R1 equal to R2. So in the voltage divider case, you would get V out equals R1 over R1 plus R2. But since R1 equals to R2, times, you would get R1 over R1 plus R2 times Vn, but since R1 equals R2, you get R1 over 2R1 times Vn, which then equals Vn over 2. So no matter what our input voltage is, if we set our two resistances to be equal, you would get half of the input voltage. And same as well with the current. Should I try to do this? Or is it too late? Okay. All right, here's a practice problem using the principles that we just learned before. So looking at this, if we want to solve for the voltage across each resistor, we can just use a simple KCL method to find that. So let's establish our node first. I'm going to select node 4 here. So our current is going to start there and wrap around our entire loop and then finish again at loop 4. So it flows here, here, and back there. So we know that the current is actually the same through each of these resistances. So all we need to do to find the voltage across each resistor is to find this total current. So let's use KVL to solve that. So here we have, since this current goes into the negative terminal, we have -9 plus I times R1 plus I times R2 plus I times R3 equals 0. We can then combine like terms and move the 9 to the other side to say I times R1 plus R2 plus R3 equals to 9. So 5 plus 3 plus 10 equals 18. So I times 18K ohms equals 9 volts. We can then easily see that the current is equal to 0.5 milliamps. So now to find the voltage across each resistor, we just multiply 0.5 milliamps by each individual resistor to find their respective voltage drops. And here are the final answers. R total is 18, I total is 0.5, and then each individual voltage drops are shown here, here, and here. You can try practicing this on your own and see if each individual voltage drops add up to equal 9 volts as they should. Okay, now we're going to do one final practice problem. As you can see, this is a little different than our last one because it has a series and a parallel combination of resistors. So we can't directly use KVL for this problem, but we can still use the same method to figure out the voltage drops across each resistor. We just have to find the equivalent resistance of the parallel combination before we use our KVL method. Since we can see that R2 and R3 are both connected at the same node, we know that these two are in parallel. And our equation that we derived for two parallel resistance is R1, or the product of the resistors over the sum of the resistors. So R2 times R3 over R2 plus R3. This will give us 18 over 9, or 2 ohms. We can then draw an equivalent circuit as follows. Two ohm, 6 volts. So now we can simply just use KVL, solve for this loop, find the total current, which is 6 equals I, and this 4 comes from the two added together. We divide 4 by both sides, and we get I equals 6 over 4, or 1.5 amps. Now we can use this current to find the voltage drop across the resistor, each individual resistors. If we draw the current in this on the respective circuit, it will look something like this. So this current is the current that we just derived at 1.5 amps. But we notice once it gets to B that it will branch off and split up into two smaller currents. We can use the rule that we just went over in a previous slide called the current divider rule to find each individual current. So the current divider rule states that I2 equals R3 over R2 plus R3 times the initial I. This results in 3 over 9 times 1.5. So you can find each individual current this way and solve for the voltage across each resistor by multiplying the current through it times its resistance. Or another way you can do this is by just using this 1.5 amps that we determined in the beginning, multiply it by R1 here to find VR1, which will equal 3 volts. And since we have a total of 6 volts here, we can determine that the voltage drop across these two resistors will also be 3 due to the conservation of energy. Here we have the system of equations that you would use on your own if you were solving this. Now we notice that V total is 6. We can find the voltage across R1 by I total times R1. And we also know that the voltage across R2 and R3 are both equal because they're both connected to the same points. So the potential difference off each of them will be the same. By using the current divider rule, we can find the ratio of currents that will go through each resistor. And you notice that more current flows through the resistor of a smaller value. This should be kind of intuitive to you, since the higher resistance means that, it will oppose current more. So again, our final answer is that there's 3 volts that is dropped across each of the resistors.